Hello, everyone. Welcome back. This is our final public lecture for the semester, for the school year, actually. So thank you all for being a very dedicated audience and being with us during this whole process. So hopefully we will be back together in person at some point. So today we have a talk with Dr. Carol Paty from the University of Oregon, and she will be talking about searching for habitable ocean worlds. So, Dr. Paty, thank you.
Great. Thank you so much. And thank you for having me here today. I feel honored to be giving your last lecture of the term. So yes, I thought I would give a bit of a different talk than I usually give. So I hope this comes across well, and definitely feel free to add some questions. I'm happy to take them at any point. So yeah, today I'm going to talk to you about searching for habitable ocean worlds. And to begin, I thought I would first start with thinking about what do we mean by habitable worlds? This is not a new phrase. The idea of the habitable zone or the Goldilocks zone around a star has been around for decades and decades. The idea being that, of course, the sun or the star at the center of the stellar system provides heat and a source of light. And habitability, or this idea that the ingredients for life are fundamental, and that therefore, if we're looking for habitable zones or habitable worlds, what we're really looking for are places that have liquid water at their surface. And this was kind of the canonical view for how we thought about searching for habitable zones or habitable worlds, both in our own solar system and beyond. Um, and of course, as you can see from this really nice graphic, we have a sun-like star in the middle. Anything shaded in red is considered to be too warm. Any volatiles would go into the gas phase at the surface, be trapped in the atmosphere or lost to space. And anything outside in the blue area would be too cold, and therefore those would become ices at the surface. So the idea with the Goldilocks zone or habitable zone is that in between the too hot and the too cold region is this band, this orbital region, where terrestrial planets or rocky planets could sustain liquid water on their surface, if they had, of course, a substantial atmosphere. If they have no atmosphere, then you can't sustain liquid water on the surface because the vacuum of space is right there. But given a terrestrial world with some amount of atmosphere, that in this green region, you could sustain liquid water at the surface. Now, if we're looking at stars in the galaxy, say, that are much hotter, the habitable zone gets pushed further out, right? Because that hot region, that region that's too warm at the surface of those planets, expands out because the star is hotter. And if you're looking at cooler or smaller stars, then the habitable zone creeps in, providing for orbits much closer to the star, being considered habitable or having the potential for liquid water at their surface. Again, with the assumption that these are terrestrial planets, rocky planets, that have enough of an atmosphere to enable that liquid water to survive. So that was the kind of classical picture. And then we could build on that a bit more, again, as we're thinking about with the advent of exoplanets, and not just a few, but tens and then hundreds and now thousands of exoplanets being discovered by various techniques, from Doppler radio techniques to the Kepler telescope with stellar transits. We start to think about the, things being more like an optimistic habitable zone, or maybe a conservative habitable zone. And again, this is all based on how far the planet is orbiting from its sun or its star, and how hot that star is. And of course, we've got Earth here, kind of the normalization, being our own environment, our template of a backyard that we know so well. And you see that the Earth here is aligned with our star, a moderate star, 6,000 Kelvin. And the starlight on this axis, on the bottom axis, is relative to that sunlight at Earth. So of course, Earth sits at 100% of the sunlight relative to Earth. Planets that are closer to their stars have higher amounts. Planets that are further from their stars have lesser amounts. And you kind of get the idea there. But I like this plot because it starts to, it takes what was before a rather kind of nondescript green band around the star and starts to prescribe it a bit more rigorously for different types of stars and for different distances from those stars of these terrestrial sized planets, or assumed rocky planets. And it also puts these stronger labels on them. Now, of course, we know that if planets have a really thick atmosphere, they might have a greenhouse effect that would warm their surfaces. It might push a planet to be that might have otherwise been in the optimistic habitable zone and pushed it out, like, for example, with Venus. Or it might take a planet that was a bit on the edge of being too cold and help push it into the habitable zone. So that really has been the dialogue and the discussion in planetary sciences in terms of how do we think about the search for life and how do we think about searching for habitable zones on planets in our own solar system, let alone beyond in the exoplanet population. This was so powerful that for a very long time, the mantra at NASA was actually to follow the water. And this is a slightly outdated slide, of course. This wasn't from this decade. This was from the Mars exploration roadmap from the previous decade. Um, but it's really powerful in that you can see the main driver that started things off was this notion of follow the water. We want to find the water. We're assuming that Mars is right on the edge of our own habitable zone. So maybe in craters close to the equator at summer there could be water, or maybe trapped under the ice sheet in the polar cap regions and the likes. So this mantra of follow the water pretty much drove decades of Martian exploration, from orbiters to landers to rovers. um, and you can see, of course, as I said, this is a slightly outdated slide, but there's a lot of this should look very familiar, right? We've had the Mars, um, the Mars Reconnaissance Orbiter. We've had the MAVEN spacecraft looking at the escape of atmospheric gases from Mars and trying to backtrack that in geologic time and understand how Mars lost its atmosphere and perhaps how it went from being habitable and having liquid water, as indicated by the geology on the surface, to now not having enough atmosphere to sustain large bodies of liquid water at the surface. Um, and then we've had a slew, I don't want to say a suite, but a slew of various rovers, from Spirit and Opportunity to the Curiosity rover, and of course now Mars 2020, which has landed and actually just this week has successfully had not one but two helicopter flights as they test out the new Mars helicopter that they brought along with it. Um, ExoMars on this slide has actually slipped to a 2022 launch. But otherwise, this roadmap for Martian exploration was really dictated by following the water, then looking for and exploring habitability on Mars, and then looking for signs of life. And this was all well and good, and it led to a very rich and a very um, detailed mission plan for sending missions basically every launch window, which is every 2 years, to Mars, um, to follow this roadmap for following the water, exploring habitability, and eventually seeking signs of life. And then you can see at the very bottom there, it says prepare for human exploration. Because, of course, if we're going to send long term visitors to Mars, having a localized supply of water is actually quite critical. But I just thought this was nice because it really embodies how NASA had been thinking about habitability based on the Goldilocks or habitable zone, and how it really dictated, shaped, structured the planning, the cadence of missions, and the types of missions that we were sending to Mars for decades. Of course, things began to change a bit as we began to study the outer solar system. And this image is actually a really nice graphic that shows, when we think about how much water there is in the solar system, beyond the ice line, beyond that blue line in the habitable zone, is there's actually lots of water. All the icy moons have lots and lots of water. Now, the question is whether it's liquid water or not. But at Earth, if we just think about it in terms of scale size, this image is to scale, and it kind of maps out, how much by volume. If you think about the Earth's size, how much water is there by volume? And it's actually not a very large amount. If we look to an icy moon like Europa, which is much smaller than the Earth, as you can see from the graphic, um, it has proportionately much, much more water than the Earth has. And even compared to the Earth, it has about 2.3 to 3 times as much water as is present on the entirety of the Earth. So, as we began to explore the outer solar system with the Voyager spacecraft and then later with Galileo and Cassini, our view of where water is distributed in the solar system began to evolve. Um, and you can kind of think about, and this graphic for Europa, of course, came about from the fact that we actually realize that liquid water might not just be something that exists at the surface of a world, but that a subsurface ocean of liquid water could be equally powerful and equally habitable, especially as our exploration of our own Earth and the deep sea of our own Earth revealed that life actually could thrive at the bottom of the ocean, far away from sunlight, much, much too deep to be receiving energy for photosynthesis or other types of sun-based sun sourced energy, but that the black smokers and various volcanic activity along the trenches and deep down in the ocean and the ocean crust were providing the energy necessary for life and probably provided the energy necessary for life to begin and evolve on the earth as well. So suddenly our mentality began to shift away from liquid water at the surface to where might water be distributed in the solar system, and in fact, is subsurface water also a really viable place to be looking for habitability or to be characterizing as potentially habitable? So, if we begin to look at the distribution of ocean worlds or potential ocean worlds in our own solar system, again, to scale here, we see Enceladus, Dione, Earth, which again is a planet, not a moon. Um, but by volume, it actually doesn't have a ton of water given its size compared to even a tiny moon like Dione or Enceladus, even, which has less. But Enceladus is only 250 kilometers across in radius compared to the Earth. So it's actually a significant fraction of it is water. And then we look to the larger icy satellites like Europa, Triton, Callisto, Ganymede, Titan. These are all icy worlds, icy moons orbiting large gas giants and ice giant planets in our outer solar system, which have the potential, based on the amount of water by volume, to have significant amounts of liquid water potentially if we have a mechanism to keep that water liquid in the subsurface. So I think this is just a really useful graphic for, again, thinking about the distribution of water in the solar system, and now having to tune ourselves to think about, well, okay, but a snowball does not constitute a habitable environment, so a completely frozen icy moon might not be very habitable. But if there was a mechanism to keep some amount of that water liquid in the subsurface, then we're in business. Then we're starting to think about habitability in the outer solar system, far, very far from the classical habitable zone. So fast forward a little bit further in time, and we have this lovely graphic, and this is really an eye chart, so don't try to read all the fine print, but it's a lovely graphic that NASA has out that really maps the possible ocean worlds in our solar system in great deal, and it characterizes them in terms of their distance from the sun, in terms of whether or not we think that there's liquid water or we know that there's liquid water on the subsurface, and I'll talk to you a bit about how we know that now. um, and just, in general, how interesting they might be to visit, to understand better, and how suitable they might be for hosting life. So of course we have Earth at 1 AU, and it's listed as being active. Oh, it's got a dynamic ocean and it's known to support life. Thank goodness the Earth is habitable. We are in luck. um, and this chart kind of goes in distance order, right? So we're marching our way outward through the solar system. And we see up next is Europa and Ganymede and Callisto. These are three of the larger Galilean moons orbiting Jupiter, or the larger moons orbiting Jupiter. And then we get out to Saturn and we see Enceladus, that small icy world, again, only 260 kilometers in radius, but incredibly active. We see ice geysers spewing material out of those southern cracks, southern polar cracks down here. And we've detected oceans there. And again, I'm going to tell you a bit more how we detect them in just a moment. And then we have Titan, the largest moon of Saturn, also has subsurface water, but it's a bit tricky at Titan because of the fact that it seems, based on what we know about it, that that subsurface water might be sandwiched in between two layers of ice, which it turns out is not very good for habitability. If you're in a subsurface ocean, much like in our own deep ocean, you need to be in contact with the rock. You need to be in contact with maybe some sort of geothermal activity or thermal activity, which allows for a chemical battery, as it were, to support life, as opposed to a solar photovoltaic battery, which we think about in terms of photosynthesis and life at the surface of the earth. Um, oh, I see a question in the chat. Hold on. Why do I think the distribution of water in the solar system ended up this way? Um, okay, so that's a really great question. A lot of this has to do, a lot of the distribution of water in the solar system has to do with how the planets formed in the early circumstellar disk around our sun, and the fact that if you're too close into the star when you're forming as a planet, it's just so hot that the volatiles, not only won't they be liquid at the surface, but they're going to be blown away as the planets are trying to form. So there's not a lot of volatile gases in the inner solar system, like say at Mercury distances, for example, because it's just too hot. The further out in the solar system you go, those volatiles are essentially frozen. And so as those bodies are forming, that frozen material, those small ice grains and the likes are part of that formation process. And hence, those smaller bodies, even though they're smaller, but further out in the solar system, can contain a lot more ice. I don't know if that fully answers your question, but it comes down to how, as the planets and their even around the planets, their circumstellar or their circumplanetary systems of moons and rings are forming. If it's cold enough, the volatiles stick around through the formation process and end up as ice at the surface of these moons. Whereas the closer in you go in the solar system, it's just so warm that the volatiles are being stripped away throughout the formation process. Now, of course, that doesn't get into the complexities of planetary migration and the likes, but actually the distribution of volatiles and the distribution of materials in general in the solar system give us clues as to how it evolved in time and how planets may or may not have migrated through their evolutionary process over the last 4.5 billion years. Okay, so in terms of exploring ocean worlds, this is a great chart that was put together for the roadmap to ocean worlds, which was a study published in 2019. And this really tried to take our understanding of ocean worlds, which again I'm going to get to in just a second, but put it in context throughout the solar system. And there's a lot going on in this chart, and I won't walk you through all of them, but the idea is that we have, in fact, been exploring and discovering ocean worlds for quite some time. We had the Voyager spacecrafts, which didn't discover ocean worlds, but discovered icy worlds and discovered indicators and clues that there might possibly be subsurface oceans on these bodies, just by nature of taking photographs of the surfaces of these moons and seeing that perhaps the surfaces were quite new, they didn't have a lot of cratering on them, which meant that there had to be some thermal processing or geologic activity that would allow for these pristine and young surfaces to exist on these moons. Um, Now, Galileo, that was really the moneymaker for ocean worlds. Galileo discovered the first ocean worlds, and I'm going to walk us through that in just a moment. Cassini followed on Galileo's footprints, except instead of orbiting around Jupiter and exploring the Galilean moons, Cassini went to Saturn and revealed a whole suite of new and exciting things about the moons like Enceladus and Titan, and their evolution in the Saturn system. We had New Horizons go out to Pluto and now beyond into the Kuiper Belt. And as you might remember, it got to see a contact binary in the Kuiper Belt that was named Arakoth. And then Dawn went to Ceres and Vesta in the asteroid belt, so much closer to Earth, and discovered that there may even be ocean worlds or icy ocean worlds potentially within the asteroid belt in the dwarf planets of Ceres and potentially other objects as well. And so all those are color coded on this by object in terms of ocean worlds that have been confirmed. And again, we're going to talk about those in just a moment, like Europa and Ganymede, and actually Callisto can be confirmed now as well as Titan and Enceladus. And it also breaks things down in terms of how do we actually define how we explore ocean worlds. So one is that we identify it's an ocean world, right? So we have an energy source. We understand that there's a thermal source that's enabling a sustained ocean. We see an ocean signature, and I'll talk about how we do that. And then we characterize them. And by characterizing the oceans, what we're saying is we want to understand how deep they are beneath the ice. Are they in contact with the rock interface? Are they saline? Do they have salt in them, or are they just pure water? Um, and then we move from there. Once been able to characterize the oceans, then we can start to do things like assess the habitability or the potential habitability of these subsurface bodies of water. And again, then we're starting to look into, is there contact with the rock ocean interface? Is there energy for life within the system, not provided by the sun, but provided by some other sort of chemical reaction or geothermal reaction that's providing that oh so necessary energy for life? And then, of course, are there the physiochemical conditions for life sustainable in that subsurface body of water? And lastly, if you move on to the search for life, there we start the murky job of trying to indicate or determine what a biomarker would look like in another world that would answer definitively or possibly whether or not life exists in that space or not. So this is, like I said, it's a chart that's just full of information and depth, but it really goes to show just how much the thinking has evolved from the 1960s, 70s, 80s, 90s to a critical event in 2000 that changed the roadmap, that changed the script, and has pushed us into expanding the habitable zone to all of these icy worlds, even well beyond what was classically thought about as the habitable zone. So how do we go about detecting a subsurface ocean? How do we go about saying somewhere beneath that frozen crust, in fact, resides an entire global ocean that's salty and might even sustain a habitable environment for long enough to evolve life? And I like to call this better living through space physics. Okay, so I am a space plasma physicist. I model charged particles interacting with planetary magnetic fields. That's kind of my jam, kind of the thing that I spend my days, evenings, nights, weekends. We won't get into all of that, but that's what I spend my time doing. So, what is space physics? And again, I know that you all come from different backgrounds. Broadly speaking, space physics can be broken into three categories. We can think about it as being solar and heliophysics, and this is the study of the sun, solar variability, the sun cycle, the structure and dynamics of the solar wind as it propagates throughout interplanetary space in our solar system. And then finally, its interaction with the interstellar medium, what we call the Heliopas, or the edge of our solar system, the edge of the region around our star that's dominated by our star's wind. At that boundary, all the average stellar winds of all the stars in the galaxy meet up with that and create a pressure boundary. Anything outside of that is what we refer to as interstellar space or the interstellar medium. And anything inside that boundary is our solar system, is the part of the space around our sun that's governed and dictated and dominated by our sun and the stellar wind sourced from our sun. So that's solar and heliophysics. Then I've highlighted here magnetospheric physics, which is the flavor of space physics that I do. And this is the study of plasmas, magnetic and electric fields, and current systems in the magnetic fields around the Earth and other planets. And I'll show you in a moment how it's this branch of space physics that helps us detect subsurface oceans. And then there's aeronomy, and this is the study of the ionized and neutral upper atmospheres of the Earth and the planets and their interactions with their respective space environments. Aeronomy covers a lot of ground, well, not literally ground, a lot of atmosphere from kind of above the troposphere and on up through the ionosphere of a planet, and how the interaction with the planet's magnetic field and the solar wind affects that upper atmosphere of the planet. So, in terms of planetary space physics or magnetospheric physics, probably the one thing that you're most familiar with is something called the aurora. Even if you haven't seen it, I'm sure that you've probably all heard of it. And I thought I'd share this video with you of some aurora we photographed or did a time lapse of in Iceland a few years ago, back in the before times when we could all travel to conferences. And here we see just a beautiful example outside Reykjavik in a very small town where we see the northern lights, the aurora, dancing for us above the clouds in greens. These are 5-second interval images. Sometimes you see a hint of pink or magenta at the bottom of those green flapping curtains of light. and it's absolutely incredible. This was the first time I really got to see in person really dynamic and vivid aurora. And if I hadn't already been a space physicist, I probably would have signed up and gotten my membership card after this particular night, because it really was striking and a beautiful expression of the dynamic environment that surrounds our Earth, driven by that stellar solar wind interacting with our Earth's magnetosphere. So, just again to give some context about magnetospheric physics before we dive into the icy world physics, um, I said this that magnetospheric physics is really driven by the solar wind. So we have the sun, and you see this nice picture of the sun in eclipse, and an eclipse is one of the few times where we can see unaided the atmosphere of the sun, that outer atmosphere known as the corona, which is so hot that it's streaming away from the sun at hundreds of kilometers a second. It's also so hot that the electrons have been separated from the atoms of hydrogen. That's the main composition of the sun. And so we're left with a plasma of protons and electrons streaming away from the sun at hundreds of kilometers a second. And because it's a plasma, because these are charged particles, they carry with them some of the magnetic flux from the sun's magnetic field. That magnetic field of the sun actually structures the flow of those charged particles away from the surface of the sun. And you can see that by what appear to be tendrils, or these structures in the streaming solar wind. Those are structures dictated by the magnetic field of the sun that shape and govern the way in which the solar wind escapes from the surface of the sun. Now, by the time that plasma, that mixture of positive and negative charges threaded with the magnetic field of the sun, reaches the Earth, it's moving still at about 400 kilometers a second. The average density is about 5 particles per cubic centimeter, otherwise known as the vacuum of space. But to a space physicist, that sounds relatively dense compared to the further out distances in the solar system, where it goes down to zero point 0.1 particle per centimeter. Um, and the magnetic field that it's carrying with it at the Earth is anywhere between 5 and 10 nanotesla total, which compared to it pales in comparison to the 31,000 nanotesla you and I are walking around in right now at the surface of the Earth. But anyway, I digress. This is the solar wind, charged particles carrying with them magnetic flux from the sun, streaming at the planets at hundreds of kilometers a second. And what happens when that solar wind interacts with a planetary magnetic field? Obviously, the Earth does not have a bar magnet in it, but just as a diagram, the Earth's field is roughly dipolar, especially the further away from the Earth you go. When you combine those charged magnetized particles from the solar wind and they run into this magnetic obstruction of the Earth's magnetic field, what we're left with is a really dynamic environment around the Earth, known as the magnetosphere. Right, so out here in the distant region, this bright yellow boundary, that's the bow shock. That's because the solar wind is moving supersonically and superalphanically, which is kind of like the sound speed, but for um, magnetic waves moving through a plasma. And so when things move at a super magnetosonic speed and see an obstruction, they can't send information back upstream to say, hey, flow, get out of the way, there's an obstruction. And instead of getting a wave there, like you would get, say, from a river flowing over a rock, where you'd see a standing wave around the rock where the water's being diverted around the rock as the river's flowing by, here that solar wind flow creates a shock, a standing wave, a standing shock. And that shock translates some of the energy from the solar wind from dynamic energy, kinetic energy, to thermal energy, and leaves us with this shocked, turbulent, hot plasma in between the bow shock and this, what's labeled in this flashy boundary as the magnetopause. So you've got the shocked solar wind plasma in here, then the magnetopause, and inside the magnetopause is where the Earth's magnetic field takes over. It kind of provides this magnetic screen or shield, as it were, from the dynamic solar wind, and really, for the most part, protects the inner magnetosphere, the inner near space environment of the Earth, from most of those high energy charged particles that the solar wind is streaming past the Earth. Now, it's not perfectly keeping it out. This whole system is dynamic and responsive to changes in the solar wind, and that's how we end up with that beautiful light show, the aurora, the northern lights, occurring over the poles. Is as our magnetic shield responds to changes in the solar wind, it essentially leaks in some energy and propagates that energy down to our atmosphere, where charged particles collide with the atmosphere, phosphoresce, or essentially energize the atmosphere, and relaxes back down, releases light. So this is all well and good. Now I've given you space physics in 3 slides, but I still haven't told you how space physics or magnetospheric physics relates to subsurface oceans. So take this picture in your mind of the magnetosphere and how magnetospheres and charged particles and magnetic fields are related. And now let's take a look at Jupiter. Now Jupiter, pictured here on the right-hand side, is a large gas giant planet. It has a very strong magnetic field that extends about 100 Jupiter radii out towards the sun. For scale, the Earth's magnetosphere only goes from about 8 to 10 Earth radii away before that solar wind compresses it in and creates that shock upstream. But Jupiter's magnetosphere is expansive. The field is strong. The solar wind has become more diffuse as it propagates out from the sun. Jupiter is located at 5 astronomical units. And Jupiter, you see here, I hope you can see, highlighted in red, has an internal plasma source that's not plasma coming from the solar atmosphere, but it's plasma coming from the moon Io, which is so volcanically active. You can see a volcano erupting here off of the limb that was captured by the New Horizons flyby in 2007. But Io constantly has volcanic activity erupting off of its surface, and it creates a plasma source that creates this what we call a plasma torus or a plasma donut that's feeding Jupiter's magnetic field with plasma constantly on the order of about 1 ton per second, consistently. And Jupiter's magnetic field is rotating very, very fast every 10 hours because that's Jupiter's rotational period. And so you have this plasma that's feeding them Jupiter's magnetosphere and helping it expand out against the solar wind out to 100 Jupiter radii, and embedded within Jupiter's magnetosphere that's rapidly rotating and streaming past these moons are the Galilean moons, Io, Europa, Ganymede, and further out, Callisto. So let's see. Oh, there we go. And Jupiter has its own aurora as well. We see this beautiful northern lights, if you will, of Jupiter, the Jupiter auroral oval, that's being dictated by not so much the solar wind in this case, but the addition of plasma from that volcanically active moon Io, and how that plasma has to get accelerated and essentially centrifugally spun out of the system over time. Then we have these auroral footprints. This is Io. This maps magnetically to the location of Io, Europa, and Ganymede. So again, that's these pink magnetic flux lines that map magnetically from the icy moon all the way down to the ionosphere of Jupiter. And you can see there's kind of a teleconnection via electromagnetic currents that enables these bright auroral footprints, which orbit around at the orbital speed of the moons. So really neat stuff. And then just for good measure, some of the moons have their own diffuse atmospheres, and the connection with Jupiter's magnetosphere creates aurora at the moons themselves. This is Ganymede, and this is the aurora at Ganymede. So similar to the way the sun and its magnetized plasma flow past Earth creates aurora at the Earth, we have the icy moons of Jupiter, which are being swept by Jupiter's rapidly rotating magnetic field, generating aurora in the diffuse exospheres of these icy moons. So the takeaway here is that magnetospheric science is alive and well. Magnetospheric physics is alive and well at the gas giants, and it is interacting with the moons themselves. But I still haven't told you about how it is that we detect subsurface oceans on these moons. So for that, we're going to take a quick shift and talk about Europa's magnetic personality. And so here's that same cartoon where we have, except now Jupiter's off to the left-hand side, and that somehow feels better for my symmetry. So we've got Jupiter here, its strong magnetic field rotating around every 10 hours. We've got Io in all its volcanic glory, adding plasma to the system. And then about twice as far away from Jupiter as Io, we have Europa. And Europa is feeling this magnetic field from Jupiter rotating past it. And it turns out, due to an incredibly convenient geometry of Jupiter's magnetic field, it's actually feeling a magnetic wave sweep past it as Jupiter is rotating. And how can that be? What do I mean when I say a magnetic wave? Well, Jupiter's magnetic field, its dipolar magnetic field, is tilted 10 degrees off from its rotation axis. Now the moons orbit around the rotational equator of Jupiter. And that means that Jupiter's magnetic field is kind of wobbling because of that 10-degree offset. It's wobbling every rotational period, creating an up and down magnetic wave at the orbital location of the icy moons, in this case specifically of Europa. And you can see here, I've already given you a hint as to what's coming along in terms of Europa's magnetic personality, because I've drawn some magnetic flux, or not me, the artist, who is way better at this than I am, drew some nice magnetic flux or magnetic field around Europa. So what do I mean by the fact that Jupiter's magnetic field is oscillating up and down? Well, here is a graphic, and it will make you dizzy if you stare at it too long. But in red, we see the orbital path of Europa going around Jupiter. The red axis is the rotation axis, and again, the red oval is the equatorial orbital plane of Europa. And then in turquoise, or in cyan, what you see is the Jovian magnetic equator, because of the fact that it's tilted 10 degrees off from the rotational axis and the rotational equator. So every rotation of Jupiter, plus a little bit of extra motion from Europa's orbital motion, we see the magnetic equator is sweeping up and down over Europa's orbital location. You can see that really well right now on the edge here, that the magnetic equator is sweeping up and down over the orbital equator of Europa and changing the magnetic wave, or the magnetic field orientation and strength that's felt by Europa as it moves around its orbital path. Now, something that's a little harder to tell here is that Europa's orbit is eccentric. It's not a perfect circle. And because of that, it means when it's at its apogee, or the apoapse of its orbit around Jupiter, it's at its furthest point from Jupiter. And that means the magnetic field is the weakest, because dipole fields fall off as 1 over r cubed. And when it's at its perigee, or its closest part of the orbit around Jupiter, it feels the strongest field of Jupiter. So we actually end up with a couple of different magnetic waves, one being in terms of the strength as it's moving around on its many-day orbit, and one in terms of the orientation and strength due to the rotation of Jupiter and that oscillation of the magnetic equator up and down over Enceladus's orbital path. I hope that made sense and didn't make you too dizzy. I'm just going to do a freeze frame of that now, and basically again remind you that the dipole is tilted 10 degrees relative to the rotation axis. And something I didn't really get into, but because of that plasma source from Io, Jupiter's field isn't perfectly dipolar. It actually gets a little stretched at the magnetic equator. And so it's a bit more noticeable, the field changes, the magnetic wave that Europa experiences, because of the fact that it's not so beautifully and perfectly dipolar as in this image, but in fact a little bit more squished and a little bit more stretched and pointy at the equator due to the centrifugal forces basically pushing out the plasma from Io and creating what we call a plasma disk in the magnetic field that stretches the magnetic field at the magnetic equator of Jupiter. Okay, so here we go. What is going on in this figure? We're probing Jupiter's interior, or probing Europa's interior, excuse me, with Jupiter's magnetosphere. And these are a set of observations in the magnetic field taken by the Galileo spacecraft at various flybys of Europa. Don't worry about what the numbers mean. That just has to do with the fact that Galileo was orbiting Jupiter, and on the 4th orbit, it happened to pass by Europa, so that's the E4 orbit. On the 14th orbit of Jupiter, Galileo passed by Europa again, so it was labeled E14, and on the 26th orbit of Jupiter, it flew by Europa again, and so that's E26. But what are we actually looking at here? And just in case you can't see it, because I know it's small and grainy because it's old data that's been scanned here. But you were looking at the magnetic field observation in the 3 vector components, Bx, By, Bz, relative to Europa, and the total magnetic field strength. And I'm going to give you a hint. What are we looking at here? This is from Margaret Kevelson's paper in 2000. We're looking at a paradigm change. We're looking at a shift, because what we're looking at is the discovery of Europa's global subsurface ocean. How did we do that? Again, it's better living through space physics. We have this magnetic wave that I've just described to you, an oscillation, as it were, periodically changing the local magnetic field at Europa. And what Galileo saw was essentially a magnetic induction field or an induced magnetic field that comes from having an oscillating magnetic wave pass through a spherical conductor. Now, if we only had one flyby from Galileo, it might have been a little bit hard to convince yourself that this was, in fact, an induction signal. You might think to yourself, well, maybe it's just that Europa has its own magnetic field. I mean, I haven't told you this yet, but Ganymede actually has its own magnetic field, but it happens to be so far the only moon in the solar system that has its own intrinsic dipole. But still, you might see this oscillation, this perturbation in the magnetic field, which is this nice curve here. The straight line would be as if the spacecraft didn't see anything in particular magnetically at Europa. That's this black line. And this curve is what the data saw. And then there's some dotted lines, which were some modeling attempts to try and match the data. And so we saw this curve here and we said, okay, maybe Europa just happens to have a magnetic field. So we flew by again, and it was actually a little bit hard to tell. It didn't quite match the magnetic field that we inferred from the first observation in the E4 flyby, but it was kind of similar. We're like, well, maybe we just didn't properly fit, or maybe it's not a perfect dipole. Maybe it's a little more complicated than we thought. But by the time we got to the E26 flyby, what we saw was if we had assumed an intrinsic dipole from the earlier flybys, the field would have been going the other direction from what we observed. And the reason for that is, of course, that like any good inductive field responses, if you're driving the system with a magnetic wave that's changing orientation, the induced field, what I call the magnetic personality of Europa, is going to change with that magnetic wave in time. And that magnetic wave had a periodicity of about 11.2 hours because it's the 10-hour rotation period of Jupiter superposed with the motion of Europa as it orbits around. And so this was really what cinched the deal, in that we actually were able to observe the changing orientation of this induction field relative to the magnetic phase of Jupiter's magnetic field. Now, we weren't planning on this with the Galileo mission. Otherwise, we would have planned a very different mission with different flybys and a different cadence of flybys to better study Europa. But we just got lucky that we had enough flybys to fully characterize this and come to the pretty definitive conclusion that Europa had a global subsurface salty ocean. Salty because of the fact that it was just so darn conductive that pure liquid water would not have had such a strong response. So that changed everything. It didn't just detect an ocean world, but it changed the paradigm in terms of follow the water and where the habitable zone resides in this system. So how does this work from a physics point of view? Because I know some of you might be physics majors. How does it really work? And I've talked this through, so I'm just going to walk through this quickly. That periodic varying field can generate an induction field at Europa. And this provided, this only works if you have a global subsurface conductor. So either someone conveniently wrapped the entire subsurface layer of Europa beneath the ice with copper wire, or there's a global subsurface ocean residing beneath that ice shell that is providing the global conductor that's allowing this induced dipolar field to occur. And as I mentioned in the previous slides, there are actually two periodicities that exist here, plus some higher order harmonics of these two primary periodicities. There's an 11.2 hour periodicity that's essentially the rotation plus Europa's orbital motion. And then there's an 85.2 hour periodicity, and that comes from that eccentric, that non-circular orbit of Europa, moving around and feeling essentially a magnetic field a little bit further away and a little bit closer to Jupiter, and therefore seeing a change in magnetic field strength as it orbits every 85.2 hours. Okay, and this cartoon over here just illustrates if you have a primary driving field in the purple vectors, say pointing to the right hand side here, that's going to induce a magnetic moment that's equal and opposite. So the magnetic moment that it induces is going the opposite way of the driving field at that given time. And again, this is a time variable driving field because it's a wave. And so here, the induction dipole, the dipole moment is this way, and therefore the induced dipolar field looks like this in the blue. This is time dependent. So when the purple field points the opposite direction, it flips and changes the direction of the induced field to exactly opposite the driving field. So the induced dipole, if you have a dire need to see the equations, I thought I would be doing a disservice to not at least put one slide of equations up. But this derivation can be found in Zimmer and Karana et al. In 2000. And this is really the foundation of probing the interior of icy moons with magnetic fields, or better living through space physics, as I phrased it on the earlier slide. And so this is how we get from a primary driving magnetic wave, induce a secondary magnetic field, and then the total B that's over here, that's what we observe with the spacecraft, right? So we have to be able, when we fly that spacecraft by, to know the Jupiter system well enough to know what that primary driving field is, so we can remove it, isolate the secondary field, and then be able, from the secondary field, to look at what that induced magnetic moment is, and from that magnetic moment in the secondary field, be able to determine what the interior properties of that ocean are. And we do that because of two very fundamental parameters, A being the amplitude being related to the conductivity as well as the depth of the ocean, and the phase of the magnetic response. So in other words, if it's not instantaneously exactly opposite that driving wave, but there's a phase lag, then that tells us something about the conductivity and the thickness of the ice sheet. So how far beneath the ice it is, as well as how thick the ocean itself is. So those three characterizing parameters, the conductivity, the depth beneath the ice, and the overall thickness of the conductive ocean, are intertwined in how they express the inductive response in the secondary induced magnetic field. And there are many papers on how you extract or differentiate those three parameters from this singular measurement, and it's a non-unique solution. But we also have the intuition of geology, geophysics, and chemistry to help bound that non-unique space into a realm of reality which is actually quite constrained, and enables us to characterize the ocean in terms of salinity, depth, and ice shell thickness. That was a lot to take in, so I'll pause for a second. We can always come back to this at the end if there's questions. Um, so now I'm gonna just show you a little bit more about the theory on this and how it relates not just to Europa, but to Callisto, Ganymede as well. But these periodic upstream conditions act at Europa, Callisto, and Ganymede. And it's all due to this orbital geometry that they have, and the fact that Jupiter's magnetosphere creates this flapping magnetosphere due to that 10-degree tilt of the magnetic field, and creates these primary and secondary driving waves. So here at Europa, we see that this is just looking at the period of the magnetic waves that are observed. So we've got this 11.23 hour wave. That's again from the orbital motion, or from the oscillation of Jupiter's field due to the motion of Europa and the rotation of Jupiter's field. We've got this 85-hour periodic wave. That's from the orbital motion of Europa and the fact that it's in an eccentric orbit. And then you can see in here we have some other harmonics mixed in as well. For Callisto, we have a little bit different numbers involved, but again, the same exact idea that you have these different periodic driving waves that drive an induction response if you have a global subsurface conductor. The strength of those waves is shown here on these hodograms, and they're a little hard to read if you're uninitiated, but this just shows you in a two-vector space, in the Bx and the By variable space, what these waves look like. And you see it's moving between negative 10 to positive 10 nanotesla in Bx, and about negative 50 to positive 50, negative 40 to positive 40 nanotesla in By, and that's for Callisto. Europa, due to its orbital location and geometry, has more of the magnetic field moving from about, and it's closer to Jupiter as well, so the fields are stronger, moving from about negative 200 to positive 200 in By, and moving from about plus or minus 80 nanotesla in Bx. So these are real signals, and we can build magnetometers that measure down to a fraction of a nanotesla in terms of sensitivity. So if we can really understand that inductive response and piece out that induced magnetic moment, we can say a lot about the presence of a subsurface ocean, and then of course whether or not the subsurface ocean is right below the ice or really deeply buried below the ice, and how thick the ocean is as well. So it's a complicated problem. You need to be able to separate out the induction response from the total observed magnetic field. And that total observed magnetic field has some other really interesting characteristics as well, especially in the Jovian system because of all that plasma from Io's volcanoes. So there's a Jovian field, there's an ionospheric response from Europa, there's an induction response, there's a plasma dynamic response because of the plasma from Io that's also sweeping past Europa and creating an Alphane wave. Which is just another way of saying the interaction around Europa is a little bit different than the interaction of the solar wind at the Earth because it's not moving supersonically and super alphanically, but creates a standing magnetic wave. Um, and so you have to know the plasma environment. You have to know the magnetic field to really high precision. You need to fly by a bunch of times, and you need to be able to model that external response so that you can isolate the induction response. And then, if you really want to characterize the ocean and not just have a rough idea of what the ocean looks like, you probably want to have a bunch of flybys at different magnetic phases and the likes so that you can perform a giant inversion and solve for what the interior parameters really are. And to do this, we have the Europa Clipper mission. This is NASA's next big flagship mission, and it is due to launch in fall of 2024. So stay tuned. If you're still in Florida in fall of 2024, it should be a really big, flashy launch because it's going to have to launch on a really, really big rocket, which is always the best kind of rocket to watch launch. So this mission has been near and dear to my heart. I was on the original instrumentation proposal teams to put a plasma detector and an ice penetrating radar on this spacecraft. The magnetometer is actually at the end of this boom up here, which put the magnetometer as far away from the spacecraft as possible because the spacecraft makes its own magnetic fields that we have to deal with from the currents flowing through the solar panels and the electronics and the likes. And then these are the ice penetrating radar actually has two different antenna systems because there's two different waves that are being used. These are the long antennas, these long guys here, and then these guys are the short antennas for the other frequency of the ice penetrating radar. So stay tuned. It's going to be a very exciting launch and about a 6-year journey, 5-year journey, depending on exactly how and when we launch in the launch window. And then we should be getting to Europa to understand and fully characterize the subsurface ocean that was discovered in 2000 by a few paltry flybys of the Galileo spacecraft. Oh gosh, I'm running a bit long, so I'm going to pick things up just a tiny bit. So that's the Clipper mission. It's very exciting and on the near horizon. I want to talk to you about one other mission that's near and dear to my heart and another icy ocean, potential icy ocean world, and that's the Trident mission to the moon Triton, which is um, in orbit around Neptune. Oh my goodness. Trident was a phase A selection for the discovery competition and NASA is going to make the decision as to which of the 4 phase A studies they selected will actually fly as the next discovery mission in June. So stay tuned to see if Trident is in fact our next discovery class mission. Trident basically helped us learn Jupiter and Europa, I'm sorry, helped us learn so much about the potential for ocean worlds and icy ocean worlds in the outer solar system. So this journey that we've mapped out with the Trident mission is one that was inspired by ocean world discoveries made in the Jupiter system. But it's really been enabled by what we've learned at Neptune and about Triton. And it's just going to be an incredible opportunity to study this incredible world. So here we have Neptune. It's a different environment. Neptune's rotation axis is tilted at 28 degrees from the ecliptic, but the magnetic axis is tilted another 47 degrees from there. So what you end up having, and it's also off-centered from the center, meaning that there's higher order quadrupole moments, which just means it's a complicated field. And then we have Triton. Triton is an insanely complicated orbit. And by complicated, I just mean it's not in an orbit it could have formed in. And we talked about this earlier in the lecture. Triton is actually not a moon that formed around Neptune, but in fact is a captured Kuiper Belt object from much further out. You can kind of think of Triton as kind of like the rogue cousin of Pluto, which flew too close to Neptune and got captured in this really highly inclined elliptical orbit around Neptune. And in that process, experienced such intense tidal heating to circularize its orbit that it completely melted and differentiated the interior, completely resurfaced the icy shell of the moon, telling us that it's a because we can see it's a very young surface. We know that there was intense thermal processing of that surface, and we believe, strongly believe, that due to this high inclination orbit, there are obliquity tides as it orbits around Neptune, which enable the long sustained um, melted subsurface ocean to be present at Triton. Now, we've only flown by Triton once with the Voyager 2 spacecraft in 1989. Oh, a long time ago, and we didn't fly very close to it. We couldn't measure any magnetic fields. We were tens of thousands of kilometers away, but the images we received indicated to us that it was a really novel and young surface, highly dynamic, and that compositionally it really resembled a Kuiper Belt object and not something that could have formed natively around Neptune. And so we decided that this would be a really incredible system to study. Before, you saw those nice oscillating videos where Jupiter's field is sweeping because of the 10-degree tilt in the magnetic field, a reminder that Neptune's magnetic field is so incredibly tilted relative to its magnetic axis that it does more than a small oscillating dance. It creates a very large magnetic wave to drive the potential induction field at Triton. That and the fact that Triton's highly inclined orbit also creates another wave pattern, 141-hour wave pattern. Sorry about that. These driving waves are really illustrated in this figure where we see there's the 141-hour wave, this guy, driven by the highly inclined orbit of Triton. And here's the 14-hour wave that's essentially due to the rotation of Neptune's magnetic field. Oh, and that little red guy that's just zooming through your screen, that's Trident. That's Trident flying by Triton at just a few hundred kilometers above the surface to measure the induced field and tell us whether or not it actually has a subsurface ocean. And incredibly, due to this geometry and these strong driving waves and the lack of plasma that's present up here because Neptune's magnetosphere is relatively empty and is actually generally quite far away from the location of Trident due to the orbital inclination, we have an opportunity with a single flyby of a very inexpensive mission to detect and characterize the subsurface ocean of Trident on a single pass. So I'll leave you with this in mind. That Trident is a discovery mission to Triton, and its discovery mission just means it's a small, inexpensive mission compared to these large flagship missions that take decades to plan and billions of dollars to fly. Trident is less than $1 billion mission. It's about a $500 million mission to fly to the deepest part of our solar system, the furthest distance planet, see this large moon, which is actually a captured Kuiper Belt object, and answer these four fundamental questions, which I don't have time to talk about in detail, but I've covered the main one, the exciting one to me, which is Triton an ocean world? How does the landscape keep resurfacing through all these geologic features, plumes, geysers that were observed back in 1989, cantaloupe terrain, and thermally processed ice surface, indications of icy volcanism? What drives Triton's plumes? Is this a photo volatilization on the surface due to the long seasons at Triton, or is it due to interior convection and interior processing? And why is Triton's ionosphere so intense? I didn't even get to talk to you about that, but Triton has an incredibly thick ionosphere, which almost makes no sense for its distance from the sun and the fact that ionospheres are often driven by solar ionization and UV ionization. So there's just a lot of really interesting things to learn at Triton that Trident, if selected, would help us to learn and to study. So with that, I'll leave you with some conclusions and take some questions. Basically, the discovery of ocean worlds has vastly expanded the habitable zone from this kind of paltry little band in orbital space around a star that like Goldilocks is not too hot and not too cold, to really being present in so many icy worlds that are orbiting around giant planets throughout the solar system. Moon magnetosphere interactions are enabling for detecting and characterizing the oceans, and we have some really exciting missions to explore ocean worlds that are coming soon, so stay tuned. And with that, I'll open up to questions, and thank you so much for listening on a Friday night on the last day of term, basically. Oh, and I see some questions in the chat. Said, are you going to read those?
Yeah, go ahead and read those. But I just want to give you first my personal applause on behalf of everybody else. Thank you for such a great talk and learned a lot and really excited about these new ocean worlds just in our backyard, right? Like we don't have to go that far
Yeah.
for them. But our first question is from Brian Murphy, and he's asking that the method for this uh, th- that you use doesn't hold for other bodies outside of a strong magnetic field, but could aspects of this method be adapted to other ocean worlds outside of a strong magnetic field?
That's a really good question, Brian. I think part of this has caused a lot of debate. A lot of the methods that I've alluded to, the induction method, where you have lots of flybys and can use a magnetic inversion to determine the to determine the induction field and therefore the dipole field in the interior magnetic field. Um, that's been around for about 20 years. And is a really sophisticated method, but has some really strong, severe limitations in its applicability once you get to weaker fields or not as clean field interactions. But the new method we actually developed because of Trident, which is about to be published, takes things in a completely different direction and uses forward modeling to map the completely observed signal into a parameter space where we can run literally tens of thousands of possible ocean ionosphere pairs and map the parameter space and figure out where the observed signal from a single flyby resides in that space. So it's a really, there's a separation there because of the driving fields at Trident that allow us to really definitively say yes or no on whether or not there is an ocean, and then if there is one, where does it fall in that parameter space. So this newer analysis method is really powerful and will probably expand the number of ocean worlds we can explore through magnetic induction, because of the fact that it enables us so much more sensitivity by the type of method that it uses. I don't want to bore you with all the details, but it's a really neat forward modeling problem. Um, but there are some moons that it's really tricky at. Moons like Titan really suffer from the fact that they're not within the magnetosphere all the time. They're so far out that they cross over that magnetopause boundary and even sometimes out into the solar wind. And one thing we really do need in order to characterize a subsurface ocean via induction is a periodic driving wave. So you have to kind of be inside a magnetosphere with a known driving magnetic wave frequency to be able to do that analysis and understand the phase and the amplitude of those waves, because it's in the induction response in phase and amplitude space that we're able to get um, that we're able to study the conductive layer, which is the subsurface ocean, if that makes sense. So it becomes pretty tricky if you're trying to look at, say, Ceres, which is just out in the solar wind. There's not a periodic driver there. Or Pluto, also out in the solar wind, no magnetic field with periodic magnetic waves driving an inductive response that we can characterize in terms of amplitude and phase. So we are limited in that it has to be moons that are within a magnetosphere, because the magnetosphere and the rotation and orbits in the system enable us to know what those driving magnetic waves are in terms of amplitude and phase, and relate that to the induction response in terms of amplitude and phase. So there was a lot in that answer, but I hope that answered your question.
Yes, I think so. I think you touched a bit on the next question, but how much more difficult is it to detect an ocean world around trickier magnetospheres, for example, like Uranus?
That's a great question. What we found with Neptune, which I would also put in the trickier than category as well, is that in fact, these trickier geometries create more dynamic or stronger waves that don't cross through a zero null point, which you get when you have moons orbiting very close to the magnetic and rotational equator. So actually, with trickier magnetospheres or more inclined orbits, you have the potential of having stronger and more resilient waves to the analysis. So there's actually been a lot of interest in this now, and a lot of papers coming down the pipe related to Uranus's inner moons and Neptune's inner moons, because of the fact that you get these great driving waves due to the asymmetries or the complexities in those magnetic fields. So I actually think it makes it more possible. Maybe I think we cut our teeth on one of the more challenging environments at Jupiter because of all the plasma interactions and Io being a source for all this plasma, and the fact that the geometries provided a wave, but not a very big wave.
So the next question is also from Dr. Ryusei. Can we do similar experiments with the um, IMF, which I'm guessing is the induced magneto?
The interplanetary magnetic field.
Okay,
Uh,
to me, IMF is something completely different. It's initial mass function. So I'm like, wait a minute. um, do experiments with the IMF of a star and induced fields of orbiting planets. And how close do we need to be for the magnetometers to be accurate enough?
yeah, I wish that the IMF, that the interplanetary magnetic field from the sun, this ballerina effect is the idea that you kind of have the magnetic field from the sun being carried out by the solar wind. And as it moves out, because of the sun's rapid rotation and propagating out throughout the solar system, you kind of get this oscillating wave in the outward flow of the magnetic field from the sun. But unfortunately, it's not quite so laminar. It's much more turbulent and dynamic than the nice movies of the ballerina skirt magnetic wave from the sun leads you to believe. Once you zoom in on the local scale of, say, dwarf planets in the asteroid belt or objects out in the solar wind, so much is going on in the interplanetary magnetic field in terms of shocks and wave interactions, and co-rotation interaction regions where you have kind of voids and fast flows interacting with one another and creating shocks in the solar wind, that it doesn't stay so nice and um, oscillatory, I guess. So I wish it did, because there's a lot of interest in the dwarf planets in the asteroid belt, especially after the observations that Don made at Ceres, where folks would really like to study it more. But I don't think that we're quite there yet with our ability to analyze the response of the subsurface ocean to anything other than a nice periodic, predictable, and amplitude and phase wave. So the solar wind is just not organized enough to provide us with that necessary driving wave. I don't believe yet. Maybe we'll get to a better place, or if we were in orbit long enough, we could piece it together. But we haven't had a mission like that quite yet.
Okay. And well, I think you kind of touched on this again. Would the ballerina effect and the IMF be usable as a wave source?
Yeah, unfortunately, there's so much more perturbation superposed on top of that, that on the scales of the planets that it might interact with, or the moons it might interact with, it's not an organized enough wave anymore. Almost ever, but definitely anymore. Um,
So really, it's the periodic nature that kind of
that yeah, the
allows.
the rotating magnetospheres really help us out a lot in terms of driving these periodic waves, that are so, I mean, again, everything is wrapped up in that one slide that I had equations on that talked about the amplitude of the wave and the phase of the wave versus the amplitude of the response and the phase of the response. And without that very deep organization of the driving signal, it's really hard to extract from the inductive response anything that's useful or definitive, because you need that organization of the driving wave. You just need a good oscilloscope in space.
Yeah. All right. So we have quite a few comments thanking you for a great presentation, for great energy, that this is really exciting stuff. And thank you again for sharing it. And people have been excited about the topic, especially icy moons and things like that. And yeah, I think that's all the questions we have from the chat for now. Um, I just wanted to make a comment myself of when you were showing the video of the aurora here on Earth. There were a lot of clouds. I feel like when you're going aurora watching, like that's very common. So it was great that you were actually able to see it despite all those clouds. So I
Oh
thought
my
that was really
gosh.
cool.
It was really great because, going to Iceland in winter is when there's a lot of aurora, but it's also when there's a lot of bad weather. So we were kind of isolated in this small town outside Reykjavik, and that was the only clear night that we had the entire week. And it was still cloudy. It wasn't a perfectly clear night by any stretch. And we were quite honestly all in the bar after the meeting, enjoying a drink. And someone looked out the window and was like, "Oh my God, Aurora." And everyone went sprinting out of the bar. Of course, not the people from Iceland because they see it all the time, but all the scientists went sprinting out of the bar, no jackets. It was, well below freezing out. And we just stood out there for, 30, 40 minutes until the clouds rolled in and enjoying it because, yeah, the rest of the trip, it was completely clouded over. So
Yeah. All right. Yeah, so I think that's pretty much is most of the questions. And again, just comments thanking you for a wonderful talk. And I also want to thank you for a great talk. And I want to thank our audience for joining us and being a great audience. We really appreciate you guys, your questions, and your sticking with us this whole time. So thank you for bearing with us during this sort of uh, unique time. Perhaps perhaps we would have a sort of hybrid format for next year, but thank you again, and have a great weekend. Have a great rest of your night, and hopefully see you guys next semester.
and thank you all for coming on a Friday night. It was fun. Thanks for the great questions. Fingers crossed for Trident.
Yes. I think it's appropriate that if Triton ends up being an ocean world, it would go great with the theme of Triton and Neptune.